Introducing the concept of efficiency is pretty simple. It comes down to an equation where it's power out over power in. So when we talk about that, the power out is the power out from the PV device divided by the power in, which is the power from either the sun or the illumination source. So to get an accurate efficiency measurement requires that both those terms are characterized accurately. So when we look at the power out from a PV module, we look at what's called the IV curve, so the current voltage curve. The IV curve simply represents all the possible operating points that a PV device could be at for a given set of test conditions, so for a given irradiance, temperature, and spectrum. So the IV curve represents a familiar diode curve. The key difference between the IV curve of a solar cell and a typical diode curve is that on the IV curve of a solar cell, the y-axis is superpositioned in the first quadrant based on how much light intensity reaches the cell. So there's a few parameters of interest on this IV curve. Namely, they are the short circuit current, or ISC, the open circuit voltage, or VOC, and the max power point, or PMP. So if we start with the ISC, the ISC is the point on the IV curve that the PV device would operate at if a zero resistance load or near zero resistance load was affixed to the PV device. So it's the highest current with zero voltage. The ISC varies linearly with light intensity. So every change in light intensity is observed directly in the ISC parameter. ISC is not very sensitive to temperature, but it still is sensitive to temperature. It's sensitive by about 0.04% per degree C in most silicon devices. VOC, if we look at VOC, that's the point on the curve where the PV device would operate if you attached a load with very high or near infinite resistance. So it's the point with the highest voltage at zero current. The VOC is sensitive to irradiance, but not so much as, say, ISC. VOC varies logarithmically with light intensity. However, VOC is much more sensitive to temperature than ISC. So VOC on a typical silicon device is about 0.3% per degree C in the negative direction. If you look at the two axes of the IV curve, you have current and voltage. So the product of those two is power, electrical power. So if we look at the IV curve, the point in the IV curve where the product of those two is at its maximum is called the maximum power point. And it's typically found on the knee of the curve. So the PMP, the max power point, is of utmost interest to us because it ultimately is the numerator in our efficiency equation. And it's also of high interest to end users of PV. So the people who design PV systems really look at the maximum power point of all points on the IV curve because it represents what's the real power that we can actually extract from the PV device under a given set of conditions. And so another useful parameter that we can extract from the IV curve is called the fill factor. The fill factor is essentially an indication of how nice of a square does the IV curve make. And the classic example is how well does a little square fit inside a big square? So the little square being PMP and the bigger square being ISC times VOC. The theoretical maximum for the fill factor is around 0.85, and the theoretical minimum is 0.25. 0.25 would be a pure resistive load. There's a number of methods you can use to measure the IV curve, and the method you choose will likely depend on your need for accuracy, the cost or your budget, or your need for modularity. So are you measuring a single module, or are you measuring a string of modules at high voltage? Whichever method you choose, it's important to have a measurement circuit that can operate at both ISC and VOC. So those are the two extremes of your IV curve. So let's look at some possible methods, some possible circuits to measure your IV curve. The most simple is a resistive load, a variable resistor. And with this, you're essentially changing the resistance or the impedance that the PV device sees. So you alter the resistance from near zero, so ISC, and you change it all the way up to near infinite resistance, which is the VOC point of the curve. If you turn the resistor in the opposite direction, you can then measure the curve from VOC to ISC. That would be the cheapest, most basic method of measuring IV. To get a more accurate estimate of the IV curve, you would use something like a 2-quadrant electronic load or a 4-quadrant power supply. One of the reasons it's more accurate than a variable resistor is because you can get a better estimate of ISC. So when you use an electronic load, we consider the PV device an ideal current source, a constant current source. So the convention with constant current sources is to load them in voltage. So we keep the load in constant voltage mode, we step in voltage and measure current from ISC to VOC. In higher voltage strings, there's another set of options, one of which is to use a capacitive load. The capacitive load is essentially an array of capacitors, and when affixed to the PV device, we start in short circuit current, so the current spikes, and as the capacitor charges, the capacitor bank charges, voltage increases and current drops until we get to VOC. So the performance of PV devices is oftentimes modeled with equivalent circuits. The most commonly used equivalent circuit in PV is the one-diode model. So there's 4 components in the one-diode model. There's an ideal current source, which is driven by light intensity. In parallel with that, we have a diode, which gives us the diode effect on the IV curve. And then we have 2 parasitic resistances, namely the parallel R shunt resistance and R series resistance. So if you look at an ideal PV device, we know that it should have a high R shunt value and a low R series value. Both the R series and R shunt values can be extracted from the IV curve. So the R series can be extracted from the slope of the IV curve near VOC. The R shunt can be extracted from the IV curve near ISC. The R series parameter is an indication of the overall series resistance of things like bus bars, metal contacts, and maybe how well those contacts are adhered to the cell. So R shunt is an indication of the cell's overall health. If you see a low R shunt value, it could indicate several things, namely that the cell maybe has localized shunts from internal short circuits that could have come from the manufacturing process, or maybe there's micro cracks causing these shunts that were caused by mechanical vibrations, or even other degradation modes such as potential induced degradation can cause these localized shunts on the PV device and thus decrease the R shunt value. So there is an ongoing discussion in the PV industry as to which equivalent circuit to use. Do we use the 1-diode model, or do we use the 2 or maybe even 3-diode model? Oftentimes there's a trade-off between a model's complexity and its accuracy. So in most cases, it is considered acceptable to use the 1-diode model for performance modeling. The 1-diode model is useful in performance modeling. For example, if I have a weather file that describes a location's typical meteorological year, they say. And that would include things like the average sun intensity, average temperatures, wind speeds. If I have that and I have an IV curve that can be explained by a one diode model, I can put those data together to start making production estimates for a basic PV device in a given location, and I can model what's the expected energy yield in that location.